Hi, welcome to Lesson 10.4, Inscribed Angles and Polygons. So, today's lesson is going to require us to put a couple of pieces of paper on our paper so that we can look at the different scenarios that we're going to find, based on the diagrams that we're going to be looking at. So, first off, let's start with a little bit of vocabulary. An inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. An arc that lies between two lines, rays, or segment is called the intercepted arc. So as you can see here, this angle right here is called the inscribed angle, and this right here is called the intercepted arc. Now, the distance, not the distance, but the angle formed by the two intersections of the intercepted arc with the central angle, well, obviously it's called the central angle. Now, a polygon is an inscribed polygon when all of its vertices lie on the circle. So we're going to be looking at a couple of things. So what I need you to do is I want you guys to get a half sheet of paper. And in this case, instead of gluing it vertically, I want you to glue it horizontally. So we're going to be using this because we're going to have three different scenarios that's going to show you guys how it is that these theorems work or why they work. So, and this is called for the measures of inscribed angle theorem. Let me raise it up a little bit. So this is going to be for the measures of inscribed angle theorem. So we're going to be doing not necessarily a proof, but an explanation as to how they work and why they work. Now on the next page, page 294, we are going to look at the inscribed angle theorem and the inscribed right triangle theorem. So go ahead and grab a piece of paper, a clean scratch paper, glue it right in the middle of the page, and divide it into two pieces. And this is on page 294. And then the last theorem that we're going to discuss is called the inscribed quadrilateral theorem, and we're going to be doing that in this space right here. So let's take a look at all these things. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. So this is the inscribed angle, this is the intercepted arc. If the endpoints of a chord or arc lie on the same side of the inscribed angle, then the chord or arc is said to be a subtend angle. So look at this diagram right here. You have angle B, okay? You have arc AC, and you have here AC subtends angle B. We don't use that word that much, but it can show up in a couple of places. Okay, so let's take a look at the very first theorem, and we'll come back and into these specific theorems in just a bit. So the measure of an inscribed angle is 1/2 the measure of its intercepted arc. In other words, the measurement of this angle is going to be half the measurement of this intercepted arc right here. And we are going to be looking at three scenarios where we're going to be showing you why it is that this is actually true. So that's for problem number 1. That's for problem number 2. Okay, let's take a look at the next page. All right, the next theorem is called the inscribed angles of a circle theorem. So if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So as you can see in this diagram, I don't know if you can see it, let me use a highlighter. Okay, both of these angles and both of these inscribed angles intercept this arc right here. Okay, so it would be this one here and this one right here. And we're going to show you why is it that both of these angles are going to be congruent. Okay, in the second one, zoom in a little bit. An inscribed polygon is a polygon. A polygon is an inscribed polygon when all of its vertices lie in a circle. The circle that contains the vertices is a circumscribed circle. So inscribed polygon, circumscribed circle. That's for problem 3. That's for problem number 4. Okay, here's our next theorem. If a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Conversely, if one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle, and the angle opposite of the diameter is a right angle. So we're going to be looking at the converse of this when I'm demonstrating why that theorem works. And that's for number 5, by the way. Okay, the next theorem, inscribed quadrilateral theorem. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So we're going to look at the converse of that and show you how that is going to be possible. All right, so once we do all this, please go back to page 293. And what we're going to be looking at is we're going to be looking at the 3 different scenarios for the measures of the inscribed angle theorem. That's the one that says that the inscribed angle is half the measure of the arc. So let's take a look at all 3 scenarios. The first scenario, let's just draw 3 circles right here. Or what look like circles. Don't judge my circles. Okay, so 3 circles right there. Let me zoom in a little bit. Okay, let's look at case 1 first. The first case is when the intercepted arc actually goes through or is part of the diameter. All right, so I'm trying to show you here that this arc right here is going to be twice the measure of this angle right there. So here's what we're going to do. I'm going to draw another radii. Now, since this is a radius of a circle, we know that these 2 right here are actually going to be congruent. Okay, making this an isosceles right triangle. So that means that this angle here is also x. Now, one of the things that we did learn from prior chapters is that this right here is an exterior angle, and it's made up of the sum of these 2 right here. So this angle right here is going to be 2x. And since this is a central angle, this arc measure right here is going to be also 2x. Hence now, I am now showing you that this angle here is going to be half the measurement of the arc right there. Okay? So we have, now I'm going to give these names here. We have A, B, nope, not that one, sorry. A, D, B. All right, so what we have here is we have 2 times the measure of angle A, D, B equal to the arc AB, AC, sorry. Wait, AB. Oops, give me a little more space. So what we're going to do now is we are actually going to be dividing this by 2. Hence now I have the measure of angle ADB equals 1/2 the measure of arc AB. Okay, so in other words, the measurement of this angle is going to be half of this arc. So now let's take a look at the second scenario. Now in the second scenario, you are going to have the center of the circle, and the inscribed angle is going to be actually, the center is going to be inside the circle. It's going to be inside the inscribed angle. Okay, kind of like this. Okay, so we're going to call this A, D, and B. So what we're going to do here is we are actually going to use this same idea for case 1, but we're going to use it twice over here. So what I'm going to do is I'm going to create a diameter. Okay, so remember, I'm trying to look for the measure of angle ADB. That's what we're heading towards. Okay, so I want to find out what is the measurement of angle ADB. That's what we're looking for. Okay, so I'm going to call this intersection right here x. Now, based on the previous theorem that we just looked, I'm going to call this one here angle 1 and angle 2. So I have the measure of angle 1 equal to 1/2 the measure of arc AX. Okay, so this angle right here is going to be half of AX. For the same reason, the measure of angle 2 is going to be 1/2 the measure of arc XB. Now, when I add these together, I'm going to have the measurement of angle 1 plus the measurement of angle 2 equal to 1/2 the measure of arc AX plus 1/2, running out of space here, the measure of arc XB. Okay? So now what's going to happen is that both of these measure of angle 1 and angle 2, that is actually going to be the measure of angle ADB. Now I'm going to factor out a 1/2 here, and I'm going to simplify this part right here. Now if you look at this, this is bothering me. There you go. You can always just move the line, I guess. All right, so this right here is actually the whole arc AB. So the measure of angle ADB is going to be 1/2 the measure of arc AX. So as you can see, it's literally the same thing. Okay? All right, let's take a look at the third scenario. Now, in the third scenario, the center is actually not going to be included in there. So the inscribed angle is going to look something like this. Okay, so I'm going to call this one here A, D, and B. Now remember, I'm trying to figure out what that angle is going to be. So I'm going to call that angle 1 for right now. Okay, but that's going to be angle ADB. So what I'm going to do is I am going to, again, draw a line going through the center. I'm going to call this angle 2. Okay, so here's what we have. We have, and by the way, I'll call this one here C. We have, based on what we just learned, the measure of angle ADC. Okay, we have the measure of angle ADB, equals, no, keep saying the wrong letters, ADB, okay, ADB, that equals the measure of arc AC. Okay, and now we have the following. We have the measure of angle BDC equal the measure of BC. Okay. Now, here's what we're going to do. This is the part where people are going to be a little confused. Okay. So here we have ADB minus BDC. So ADB minus BDC, that's going to be that angle right there, ABD. So we're going to have the measure of angle ADB equal to the difference between these two. Okay, so we have AC minus BC. That is going to be the measure of angle AC. Okay, and I'm missing something. Oh yeah, don't forget the halves. Come on, Osuna, you're not new. Okay, so this is going to be 1/2, 1/2. Okay, and then from there you're just going to factor out that 1/2, and then we get the following, A, D, B. So as you can see, this theorem works literally for every case, okay? Whether the center is part of the intercepted arc, in the arc, or the center is in the middle, or if the center is outside of it. So as you can see, it works pretty much everywhere, okay? All right, let's take a look at the next part. And I think I'm missing something here. Measure of AX and XB. Oh yeah, this one. I made a mistake. There should be a B. Guess coffee hasn't kicked in yet. All right, let's take a look at the next part. So AC minus BC, this should be AB. AB. Man, I am making a lot of mistakes today. All right, let me zoom out so you can see everything. Yes, today's video is going to be a bit long, guys, so bear with me. All right, let's take a look at the next one. Okay, the inscribed angle theorem. Okay, so let's take a look at the inscribed angle theorem. Okay, in the inscribed angle theorem, what you have here is a circle, okay, that has two inscribed angles going to the same exact arc. Okay, so we'll call this D, A, B, and C. Okay, now keep in mind, these right here, they have the same intercepted arc. So what I'm trying to figure out is the measure of angle D and the measure of angle C. Okay, so that's what I'm trying to show here. I'm trying to show that these right here are going to be exactly the same. So part of what we already knew is that 1/2 the measure of AB was going to equal the measure of angle ADB. Okay, so this angle right here is going to be half of this. We also know that it's doing the same thing on the other side. Okay, this is going to be the measure of angle ACB. Now here's the thing, both of these, they're the same. So by the transitive property of equality, these two right here should be the same. So ADB ADB is going to equal to the measure of angle ACB. And two angles that are of equal length are going to be congruent. So angle ADB is going to be congruent to angle ACB. Therefore, that is going to be congruent to that. So that one wasn't too hard. Let's take a look at the next one. Okay, the inscribed right triangle theorem basically states that if you have a circle, okay, now I'm doing the converse part of this, okay, and you have the diameter of the circle, and you have a right triangle such that, or you have a triangle whose length, whose one of the sides is actually the, going through the diameter, then I have to show here that this is a 90-degree angle, and it's not really difficult to show. So let me just show you guys how to do that. All right, so first thing you need to realize is that arc ABC is a semicircle. That means that the measure of arc ABC is 180 degrees. Okay, let's just keep that in the back burner there. Okay, so we do know that the measure of angle C is going to be 1/2 the measure of arc AB. Okay, so this is going to be 1/2 of angle C. Okay, we also know that the measure of angle A is going to be 1/2 the measure of arc BC. So we kind of know that already. All right, so now what I'm going to do is I'm actually going to multiply both of these by 2. Okay, oh no, I could actually leave them the same if you think about it. Okay, so the measure of angle A, now what I'm going to do is I'm going to add these, plus the measure of angle C equals, now I'm going to factor out a 1/2 measure of AB plus measure of BC, okay? And then I'm going to multiply both sides by 2. All right, so when I do that, I'm going to get 2 times the measure of angle A plus the measure of angle C equal to, now let's think about this, AB plus BC, that is the measure of arc, ABC, which we already know that is going to be 180 degrees. Okay, so that's going to be 2 times the measure of angle A plus the measure of angle C. Now, when you divide both of these by 2, you're going to get the measure of angle A plus the measure of angle C equals 90 degrees. Now, if you think about this, these are the acute angles, and their sum is 90 degrees. Okay, so by the triangle, the angle sum theorem, angle B is going to be 90 degrees, therefore making that a right triangle. Okay, so that we calculated that to be 90 degrees. Therefore, it is a right triangle. All right, next page. Inscribed quadrilateral theorem. Okay, so in this one, what we have is the following. We have a circle, and we have a quadrilateral. So I'm going to call this quadrilateral here E. Doesn't have to be necessarily a square. F, G, and D. Okay, and I'm going to connect these. Just like that. Okay, now what I'm trying to show here is that the sum of the opposite angles is going to be 180. Now, I'm only going to do this for one case, but if I can show you that these two add up to 180, then I can show you that these two add up to 180. So we do know that the measure of angle E, okay, angle E, that's this one, is going to be half the measure of FD. Okay, for the same reasoning, the measure of angle G is going to be 1/2 the measure of DF. Okay? Now, I'm going to add them together. Okay, so I get the measure of angle E plus the measure of angle G is equal to, now I'm going to factor out a 1/2 while I'm at it. Okay, just like that. Now, let's think about one thing here, okay? Now, FD plus DF, that is this one, FD and DF. That is the whole circle. Now, in a whole circle, that sum, the arc measure, not the arc, yeah, the measure of the arc would have to be 360, okay? Because a semicircle is 180, a full circle is 360. So now I get the measure of angle E plus the measure of angle G is going to equal to 1/2 times 360. So the measure of angle E plus the measure of angle G is going to be 180 degrees, which now shows you that these two angles right here are going to be supplementary. All right, so after 23 minutes, we are ready for our examples. Now, I promise you the examples are probably not going to take us that long. But let's go ahead and begin. All right, here is example number 1. It says, find the indicated measure. Okay, so the measure of angle T. I want to know what this angle right here is. Now, remember, this right here is going to be twice as much as this right here. So I have to divide this by 2 to get this angle. So the measure of angle T is going to be whatever 1/2 is times 48. And that's going to be 24 degrees. Okay, so the measure of angle T is going to be 24 degrees. All right, so the measure of QR. QR happens to be this arc right there. Okay, so let's see how we're going to be doing this, because we want to find out the measure of QR. So in order to solve that, we need to remember one thing. P is the center and TR is a diameter. That means that the whole distance from here to here has to be 180 degrees. Now, because this angle right there is 50 degrees, this right here will have to be 100 degrees. So in order to figure out how much this is, we have to take out 100 from 180 degrees. So that right there is going to be 80 degrees. Okay. All right, so once again, this is 50, that's 100, that's twice of that, because this is a semicircle. All of this is 180. So 180 minus 100, that gives me this part right here to be 80 degrees. And that was example number 1. All right, let's take a look at example number 2. It says find the measure of RS and angle STR. And what do you notice? All right, so first thing, we notice here that we have the same angle being shared by those two angles right there. Okay, so this right here is also going to be 31, and the measurement of this angle is going to be twice that angle, which is 62. So the measure of RS, okay, is going to be 62, and the measure of angle STR, that's STR, is going to be exactly the same, because look, they are measuring the same as this one. They're measuring, they're both an inscribed angle to the same intercepted arc. So it will be this one right here. So that one's 31, then that one has to be 31. All right, so that's example number 2. All right, on this one, it says, given that the measure of angle E is 75, find the measure of angle F. So angle E has the same intercepted arc, which is this one right there. Now, that one has this inscribed angle and this one right here. So this angle and this angle are actually going to be the same. So the measure of angle F is also 75 degrees because they measure the same intercepted arc. All right, let's take a look at example number 4. All right, it says find each of the variables. Now, one thing that we did learn is that if you have an inscribed triangle where one of the sides is the diameter, then this triangle here was going to be a right triangle. So we know that right there is going to be a right angle, and 2x would have to equal 90 degrees, making the value of x to be 45 degrees. Now on this one, we got to remember, first of all, that the sum of the angles here is going to be 360. We also know that the opposite angles here are going to be supplementary. So if this one here is 120, y is going to equal 180 minus 120, which happens to be 60. And for the same reason, this one and this one here are going to be supplementary. So z, 180 minus, z is going to equal 180 minus 80, and that is going to be 100. Okay, so that is example number 4. Okay. All right, your camera has a 90-degree field of vision, and you want to photograph the front of a statue. You can stand at a location in which the front of the statue is all that appears in your camera field of vision as shown. You want to change your location. Where else can you stand so that the front of the statue is all that appears in your camera field of vision? So in other words, if you're standing right here, you can only see 90 degrees here. The only other place that you can stand and get the same view is anywhere that lies in this semicircle. Okay, so if you stand right there, you can still get the same 90 degrees. If you stand right here, you can still get the same 90 degrees. So basically, you can stand anywhere. Okay, you can stand anywhere on the semicircle. Writing sloppy today. In the semicircle. Just like that. All right, that concludes our video for lesson 10.4. Thank you for watching.